featureless wilderness of forest and swamp, about the size of Western Europe, is in northern Canada. Here, close to the shore of Great Slave Lake, is one of the world's largest lead-zinc mines. Pine Point. Nearly 1,000 kilometers from the nearest big city, the township of Pine Point would not be here but for this major mining operation. 20 or so pits like this one mark the sites of rich bodies of ore, and there are probably many other equally rich pockets still to be discovered on the mine property.
This is one of the pits where men work 24 hours a day for most of the year in temperatures that go from over 30 degrees centigrade in summer to less than 40 degrees below 0 centigrade in the winter. And here is some of the ore they mine. This pit's made up almost entirely of the lead sulfide galena. And in this pit, you can still see some galena, but most of it's made up of the zinc sulfide sphalerite. And the host rock to these ores is this, ordinary old limestone. Now this is a pretty average old chunk of ore. It's got about somewhere between 2 and 3% lead and maybe 5 or 6% zinc in it. That represents concentrations many orders of magnitude above concentrations in average crusts. But in fact, nature's only given us the first step in the concentration process. For this stuff to be any use at all, you've got to separate the lead sulfide from the zinc sulfide, and you've got to separate them both from the barren host rock, the limestone. And this huge and complex operation here is extracting thousands of tons of ore a day and processing it into marketable concentrates as efficiently and as economically as possible. And the organization to achieve that doesn't just develop overnight. So how did it all begin?
Until the 1940s, the south shore of Great Slave Lake was on the main trading route from Alberta to the Arctic. Early European explorers and fur traders all passed through here.
One of the most interesting groups that passed by here were the prospectors on their way north to the Yukon and the Klondike Gold Rush of 1898. And as they passed through Fort Resolution, not very far away from here, they noticed that the local Indians were using this stuff to weight their fishing nets. Grey, shiny, metallic, and very dense. It's galena. Now, any prospector worth his salt would know that galena might contain up to a few percent of silver. So naturally enough, the prospectors persuaded the Indians to take them to exactly where this stuff had been found. The surprising thing is that the Indians found the galena in the first place. It's difficult to see the wood for the trees. There's no outcrop. The whole area is being ground flat by glaciers, and there's boulders and boulder clay from hundreds of miles away dumped right on top. Of course, there's a much easier way of getting around along these little low ridges where there's not so much boulder clay, the ground's well drained, and the trees are a lot wider spaced. And it's along these ridges that the animals used to travel, and the Indians followed the animals, laid their trap lines, and they would camp in clearings. Yeah, if the Indians had chosen this particular clearing to camp in, there's no way they could have missed the galena. It's everywhere in the soil, and there's bits of white limestone there as well. But this is the only clearing in hundreds of square kilometers where you can find galena in the soil. Galena is a pretty soft and crumbly mineral. It can't be transported very far. And that suggests that if there's any lead mineralization It's just down there. The prospectors did some crude geochemical tests on the galena, but they found it was barren. There was no silver there. So they pushed off to the Klondike to pan for gold. But it wasn't very long before geologists arrived on the south shore of Great Slave Lake. By the 1920s, their mapping revealed an enormous fault cutting the ancient rocks up to the east-northeast of Pine Point. By this time, it was known that large lead-zinc deposits elsewhere in the world, sitting in limestones, were situated near to large faults. So here was all the association: lead and zinc, limestone, and a large fault. And by 1929, a consortium including Cominco had staked this area, and they set out to find out just what was beneath the ground near to the original showings in the little clearings. And this is what they found in a series of shallow pits and trenches: high-grade galena. And also salarite. Both ore minerals in cavities, in limestone, and in the limestone itself, cavities filled with calcium magnesium carbonates and calcium carbonate. So the consortium had proved the existence of high-grade lead and zinc mineralization, but to find out exactly how much was there, they had to drill. After the Second World War, the demand for metal was very, very high. The Canadian government wanted to open up the north, and these were the conditions under which a new consortium, led by Cominco, could scrape together finance, and they started a program of systematic drilling in 1948, about 10 kilometers away from here. This little ghost town and all these battered racks of diamond drill core are all that remains of the 1940s exploration. And drill core like this gives a framework of the geology underneath the swamps, the boulder clay, and the dense forest. And by linking intersections with distinctive rock types from one hole to another, enables a three-dimensional geological picture to be built up. But more important than that, the lengths and grades of intersections with the ore enable the value of the deposit to be calculated. Now around here there's kilometers of this core, and the consortium used it to prove 5 million tons of ore, running around 11% combined lead and zinc. But the main sticking point, as always, was the remoteness of Pine Point. And everything hung on long negotiations with the Canadian government to link Pine Point to the nearest railhead. And that meant building 650 kilometers of railway. So that went ahead, and the first steel was laid in 1962, and mining got the green light. In 1965, Pine Point mines were able to ship out their first high-grade ore.
An especially interesting feature of the Pine Point mine is that it isn't just one huge great hole in the ground to dig out a single big ore body. Here we've got lots of rather small pockets of rich ore scattered through a large volume of barren host rock, like big currants in an outsized bun. And in each of those pockets, there is on average between 500,000 and 2 million tons of ore.
Well, let's just look at the setting of these lead-zinc ores in a bit more detail. The host rocks are limestones. They're bedded and pretty well horizontal. And places you can find fossils in them. This block is full of remains of shelly animals called brachiopods. And this coiled shell was once inhabited by a squid-like creature. Now, these and other fossils in the rocks tell us two things about them. They tell us that the seas in which the limestones were deposited were warm and shallow, and they tell us the age of the rocks. It's Devonian, about 400 million years old. Now, this block of limestone has got a fair number of holes in it, mostly around the fossils. And limestones are fairly easily dissolved by acid rainwater and groundwater that percolates along cracks and along bedding planes in them. And where the limestone's been dissolved away, you get spaces. And into those spaces, other fluids can come and they can precipitate other minerals, like this, for instance. And I can show you a bigger and better example of that a bit further along. Well, there's obviously quite a change here. Most of the original limestone's been dissolved away, and instead we've got this complex network with open spaces in it. This white mineral is dolomite, the double carbonate of magnesium and calcium. Most of the original limestone's been dissolved away, and it's been partly replaced by the dolomite precipitated from magnesium-rich solutions which came along later. Now that was a gradual process, and it probably didn't happen all at once. It probably happened in several stages. The important thing is that the dolomite hasn't replaced all of the limestone, because this rock has still got spaces in it. Spaces into which fluids could come along later and precipitate crystals. Like, for instance, the white bladed crystals of dolomite itself, and bigger crystals of calcite. There's a complex history of different fluids moving through the rocks at different times, in different places, precipitating different sets of minerals. And you can see dolomite all over the Pine Point area. It doesn't always look like this, and there's evidence that there were several different phases of precipitation of the dolomite. You find dolomite associated with lead zinc ores in limestone all over the world. Here at Pine Point, the dissolution of limestone, the formation of these dolomite networks, means that there have been open spaces made available for ore-bearing fluids to get into. And in this block, you can see crystals of lead and zinc sulfide in amongst the dolomite. But there's another much more important and dramatic way in which the dissolution of limestone can make spaces for ore-bearing fluids to get into. We can see that in another pit. Well, here are the well-bedded limestones, pretty well horizontally layered. But if we follow the layering along here, something pretty startling happens. The layering stops suddenly, and we're into this jumbled chaos of fallen blocks. It looks rather like a landslide or a cliff fall. And that's pretty well what it is, except that here it's happened underground. Most people are familiar with the spectacular cave systems that you get in limestone country. But it happens that here, the limestones are rather thinly layered, and they're simply not strong enough to support a major cave system. So as soon as any big cave develops, it just caves in or collapses. And we're looking at the result of one of these collapses right here. And it's in this sort of material that we find the lead zinc ores. Let's go and look at a block that's been recently blasted. There are lots of spaces in between the fallen and jumbled blocks and fragments of limestone, into which the ore fluids could penetrate and precipitate the lead and zinc sulfide. Now, there's some other things here associated with the lead and zinc ores that are worth looking at, because they'll help us to understand the ore forming process a bit better. And the most spectacular one is this. It looks just like tar, doesn't it? And that's really what it is. It's natural bitumen, a residual hydrocarbon. And it's tempting to think that Pine Point might have been an oil field if nature hadn't worked to make it a lead zinc field instead. And you find this bitumen all over the place in cavities. Here it is in limestone. And there's some here in cavities in the dolomite. Now then, no less spectacular, but a bit rarer, is this rather lovely thing. Native sulfur. And that's not too surprising, really, because if you've got sulfide ores, you do need sulfur to make them. And the only other sulfide mineral here is iron sulfide. Now, that's a mineral that oxidizes very easily and it stains the rocks brown. Mostly occurs around the outside of the ore body, and it's treated here as a gangue mineral, not as an ore mineral. But it's very important because it helps to locate these rich lead-zinc ores. Well now, what about the shape of these lead-zinc ore bodies?
Many of the limestone collapse structures have a more or less vertical, cylindrical or conical shape with steep sides. The ores in them are mined in pits that are circular in plan. In other places, the pits are less regular in plan because the collapse structures were controlled by the horizontal layering of the limestone, and the ore bodies have a rather flat or tabular form. On the scale of individual pits, we can find out quite a lot about the relationship between ore and gangue minerals and host rocks. But for a fuller picture, we need to cover a much wider area. And a good way of starting to see that fuller picture is to look at the cores of rock that the company geologists get from drill holes in and between the ore bodies. Hundreds of holes are drilled each year in various parts of the mine property, providing many thousands of meters of drill core for the geologists to study.
The cores in these boxes come from a series of boreholes put down along a north to south line over a distance of approximately 15 kilometers. The cores in these boxes, these two middle boxes, are from two boreholes approximately 2 kilometers to the north and 2 kilometers to the south of me. And those two boreholes cored limestone, 200 meters of limestone. Limestones with marine fossils. They show up much better when the rock is moistened. Marine fossils here, and these are the remains of shallow water organisms. Now, these limestones are identical to the limestones which we saw in the mine pits. This borehole, put down near the shore of Great Slave Lake, about 6 kilometers to the north, is a totally different rock. It's not a limestone, it's a shale. And many of these tiny little shale fragments show the fossil remains of small sea creatures, and it's quite evident that these rocks were deposited as marine clays. Now the fossils tell us something else. They tell us that these shales were deposited in deeper water than the limestones here. The fourth borehole, that was put down way to the south, about 9 kilometers away, and it's a totally different rock. It's neither shale nor limestone. Here it is. It's anhydrite. And anhydrite is a calcium sulfate mineral, and it forms by the evaporation of seawater. So the rocks in this borehole were evaporites. So what a profound change in 15 kilometers. Open sea to the north, shallow marine limestones here, evaporites to the south. So let me try to illustrate this with a simple geological cross-section. North to south, over a distance of 15 kilometers. And we're standing approximately here. And our 4 boreholes put down from the surface, one there, another here, and the 4th right up near the shore of Great Slave Lake in the north. And these 2 boreholes cored limestone. And we know from other boreholes that those limestones form a narrow zone about 5 kilometers wide. This is limestone over a distance of about 5 kilometers. And those limestones are 200 meters in thickness. To the north, this borehole cored shale. And to the south, evaprites, and hydrite rocks. Let's call them calcium sulfate. And we know that these limestones extend as a narrow belt some 120 kilometers to the west-southwest of us, and they get progressively deeper in the subsurface as they go that way. And so, in Middle Devonian times, these limestones formed a barrier between two totally separate environments: open marine to the north and evaporite to the south. And it was in the limestones of that old barrier that our ore bodies were emplaced. So, let us look at these limestones of the barrier in more detail. Here are 4 samples of core which have been cut and polished somewhat to show their detail more clearly. This piece of core contains coral, and it was obviously part of a reef. This one has abundant shells in it, and it was probably a shell bank. And this third one is a mass of comminuted shells. It was probably a shell sand. And the fourth one, very fine-grained, difficult to resolve its detail, nevertheless, it's a limestone. So you see, that old barrier was not a simple homogeneous feature, but it was a complex. It was a complex of reefs, of shell banks, and shoals, possibly with narrow channels leading back into the evaporite lagoon beyond. Why was the barrier where it is, and why was it such a narrow feature? Well, if we go out into the country to the east of Great Slave Lake, where the Precambrian rocks are exposed, there's a major fault. And that fault runs west-southwest, straight towards us here, and along the line of the barrier. That fault displaces the Precambrian rocks, but it passes under the Devonian rocks without affecting them in any apparent way. And so, it was an old fault. The movements were all achieved before Middle Devonian times. Nevertheless, there is the possibility that there might have been slight adjustments on that fault during the Middle Devonian. A slight hinge effect, for example, almost imperceptible, but it was sufficient that when the sea swept in across the area, it dictated that there would be deep water on the one side and shoals on the other. And of course, the line of that old hinge would be the ideal place for reefs to establish themselves.
So we've got a much fuller picture of the regional setting of these lead zinc ores at Pine Point. But there are still some questions we need to ask. For instance, just how and when did the ore metals get into the reef? And what were the physical and chemical processes that control their precipitation? And for another thing, there must be plenty of ore-rich pockets still on the Pine Point property. Plenty of undiscovered currents in the bund. Now, how might they be located? Well, we'll be looking at those sorts of questions in the next program.